Okay, so in my last video on the Focke Wulf 189, there were a lot of comments asking about these weird looking propeller spinners. Now I had planned to discuss these in a future video that I'm planning that talks about propellers, pitch changing mechanisms and a couple of other things, but I've now realized that in doing so, I'd completely omitted to mention them at all in the Focke Wulf 189 video, and I now of course realize this is a mistake because they're a very interesting looking bit of kit, and there's several dozen comments asking about them. So I thought I would make this quick last minute video today to explain a bit about them and what they actually do. However, before I do that, I just want to say a truly massive thank you to everyone who has donated to the fundraiser that I've been doing for the Queensland Air Museum and their Sea Vixen cockpit. For those of you who don't know what's been going on, I've been helping the museum to raise funds to essentially build a specialized trailer that'll be used to transport this cockpit around to act as a sort of mobile educational exhibit at air shows, museums, that sort of thing. They are able to open it up, people can climb in and learn all about how this aircraft operated, and it's a great fun little attraction. The fundraiser had not even been going for a week before we hit the initial fundraising goal, which is just wonderful. I am blown away by everyone's support, as is the museum, and there were some very large individual donations that were put into the fundraiser by anonymous donors, but whoever you are, thank you. It is deeply, deeply appreciated. Now, I am going to leave the fundraiser running for the rest of the month, and that is because any extra funds will go towards cleaning up the Sea Vixen cockpit, funding extra restoration work, and purchasing the additional equipment that we will need to actually take it around on its event tour. So, you know, chairs, gazebos, signage, that sort of thing. So if you haven't donated yet, please feel free to do so now. Even if it's just $1 or $2, any little bit will help us get it on the road and get it moving, and of course, fund the equipment that we need to take it with us as well. But for everyone who has already donated, thank you so much from the bottom of our hearts. It is truly, truly, truly appreciated. Alright, enough blabbering aside, let's actually talk about the thing that I'm making this video about, which is those weird looking propeller spinners on the front of the Focke Wulf 189. So, what the heck are they? Well, to the untrained eye, they may look like some sort of aerodynamic styling choice, or perhaps something to help with the engine's cooling. But as it turns out, those spinners are neither of those things. They were a highly specialized power delivery system. In an era where most aircraft relied on either the engine's mechanical power, or complex electrical circuits, or high-pressure, leak-prone hydraulics to adjust and control the pitch of their variable pitch propellers, Argus went down a radically different path. In the simplest of terms, they essentially used a glorified air brake device to power their pitch control mechanism. So, how exactly does this work? Well, I had planned a simple explanation in my future planned video, but for this one I'm going to go into a bit more detail. But in doing some additional research the other night, I ran into a bit of a problem, and I'm glad that I did though. The problem was that secondary and tertiary sources, mostly books, forums, and websites, most of which are English language books and websites, were giving conflicting information about parts of the mechanical layout of this system. So, to avoid any discrepancies, and therefore avoid the risk of presenting you guys with inaccurate or false information, I decided to go straight to the primary sources. I went and purchased a copy of the Argus 410 engine service and maintenance manual, as well as a copy of the detailed mechanical and servicing manual for the propeller pitch mechanism itself. And after a frantic overnight translating session, I arrived the next day with a much clearer understanding of how this system works. First though, I'll just give a quick explanation as to what it does, and then I'll explain how it does it. So, although this system is used on a couple of different types of aircraft, I will just use the one from the Focke Wulf 189 as today's example. So on the outside, we of course have this weird looking spinner. Now, unlike most spinners, the whole of which rotate with the propeller hub and the blades, this one was split. The rear 2/3, starting from the base of the spinner and ending just ahead of the propeller blade roots, was mounted to the propeller hub and therefore rotated with it. The remaining front section did not. It was mounted independently on its own bearings, and because of that, it was allowed to rotate freely from the rest of this spinner. Now, due to friction at this bearing, the front section of the spinner still rotated with the rest, and if magically done in a vacuum, it would match the RPM of the propeller hub. But in the real world, we have this thing called air, which imparts air resistance, and that is where these weird-looking fins come into play. The fins essentially act as mini air brakes, preventing the front section from spinning quite as fast as the rest. For example, if the engine was rotating the main propeller hub at, say, 2,500 RPM, the free-spinning front section might only be going at around 2,450. This created a small relative speed differential of around 50 RPM between the two parts. This differential was then transmitted to a gearbox inside the spinner hub, and it was this gearbox that controlled the pitch setting of the propellers. Okay, great, that sounds relatively straightforward, but if we take a brief look at the inside of this mechanism, yeah, it's looking a bit more complex, isn't it? Which is why I am now going to walk us through the main stages of how it works. I won't look at every single individual component, but the key ones that we need to look at to understand how the power gets translated from point A to point Z, basically. With the power of editing and Photoshop, I am going to be using two illustrations to help explain this. These show the internal mechanism viewed from different perspectives so that we can see all of the vital parts. The first illustration is orientated with the propellers arranged in a 6 and 12 o'clock position, and the second illustration takes the whole thing and essentially rotates it 90 degrees counterclockwise. So as we've already established, the mechanism begins with the free spinning front section of the propeller hub. As we can see, this is separate from the rest of the hub and mounted on a bearing. And with this bearing, it is connected to a shaft, and this shaft runs into the internals of the gearbox. At the end of the shaft, we have a bevel gear. This serves as the primary transmission input, the mechanical link that imports the differential rotation of the spinner hub for use within the gearbox. The bevel gear then meshes with two counter bevel gears. Each of these are themselves physically fused to a smaller straight cut gear, or a pinion, forming coaxial double gears that are mounted on a transverse pin. This takes the axial rotation, parallel to the engine, and converts it to a transverse rotation, or in other ways, the axis is rotated 90 degrees. Furthermore, this also serves as the first mechanical reduction stage. This is essentially multiplying the torque forces so that the relatively light aerodynamic force imparted on the spinner can eventually rotate the heavy wooden propeller blades against massive centrifugal and aerodynamic forces. Now moving on through the powertrain, these double gear pinions each mesh with a spur gear. Now when the system is neutral, so when the propeller pitch does not need adjusting, this is as far as the energy transfer goes in this powertrain. The pinions of the double gears drive the spur gears, but the spur gears themselves don't yet connect to anything. Because they are driven from opposite sides of a transverse central axis, they are rotating in opposite directions around their own central shaft. This makes them key components to transmitting the rotational force required for pitch adjustment, because if you have one rotating one way, one rotating the other, those rotational forces can of course be then used to twist the propeller blades one way or the other for finer or coarser pitch adjustment. Now of course you only want to use one of these gears at any given time, because if you try to engage two, they just won't do anything, the forces will cancel each other out and the blades won't move. So you need some way of selecting which gear to use, something like a clutch. This is where the next two key components come in. You have the regulator shaft, and something which can be translated in a few different ways, but the closest approximation I can find is something called a claw wheel, or also known as a claw coupling. The claw wheel serves as our clutch in this case, and its job was to connect with and receive the rotational force of one of the two spur gears. The regulator shaft, however, had two jobs. It was the actuator that moved the claw wheel, and it also served as a mechanical governor, which is the thing that controls when pitch correction is engaged and for how long. It governs when the mechanism is required to be used. Now, in simple terms, it does this by making use of the centrifugal force that is generated by the rotating propeller hub. The regulator shaft lay coaxially along the center line. The shaft itself is not rigidly fixed. It was mounted so that it could slide forward and backward. This moving shaft carried the double-sided claw wheel, which we've already mentioned, which serves as our clutch, but it also has a spring plate, which, funnily enough, was used to hold back two sets of coaxial regulator springs. When the propeller hub is rotating, the centrifugal force would try to fling this shaft outwards, but the springs to a point were designed to prevent this movement from occurring. The claw wheel, which serves as the clutch, is attached to the shaft, so if the shaft moves, the clutch moves. So, when the engine is running at the exact RPM selected by the pilot, the centrifugal force trying to pull the shaft outward is balanced by the compression force of the regulator springs, meaning it doesn't move. If the shaft isn't moving, the clutch doesn't move, which means the whole mechanism is essentially in its neutral position. But if the RPMs increase or decrease, the centrifugal force becomes more powerful than the spring compression forces, or vice versa, and the shaft does move accordingly. This in turn moves the clutch, which then engages with one of the two spur gears. This is a really simple and inventive system, and for whatever reason later on, a second system sometimes replaced this, depending on the engine configuration, and that system would use hydraulics instead of centrifugal force to move the regulator shaft. On the whole though, it was considered less desirable due to reliability concerns, and as it's not really related to my explanation today, I'm not going to include it in this video. Okay, so we now know roughly how that section works. So let's just assume the RPMs have increased and the shaft has pulled the clutch up to engage with one of the two spur gears. This now transmits the rotational force to the shaft, but from here the rotation force needs to actually go somewhere. This is achieved by a driving screw wheel, or sometimes called a half helical screw wheel, which is connected to the very bottom of the regulator shaft. Now, it must be pointed out that this is not a rigid attachment, because the shaft still needs to move up and down along its axis. Instead, it is connected to this screw by internal splines. Essentially, the lower end of the shaft has a set of ridges, or teeth, like a gear, and the screw wheel had a slot which matched the shape of those teeth. This allowed it to receive the rotational forces while still allowing the shaft free movement along its longitudinal axis. So the main function of this gear was to act as the second gearing reduction stage. It takes the relatively high-speed rotation of the regulator shaft and converts it into a slower, extremely high-torque rotation. This screw wheel in turns meshes with and drives a second screw wheel. This one is the last common drive element before the gear train branches off to each propeller blade individually. Through this second screw wheel runs something that is often referred to in the documentation as a key shaft, and this transmits the torque forces to two identical worm screws which are fixed upon it. These worm screws then drive two intermediate screw wheels, which act as the final reduction stage, and in turn are connected to two more worm screws, which themselves then drive two large worm wheels. These wheels are what actually rotate the propeller blades and thus adjust the propeller's pitch. The final stage here also provides a vital safety feature, which is self-locking. Because worm gears can't be back-driven, they physically prevented any aerodynamic forces from moving the blades out of their set position when the gearbox wasn't actively being used. Furthermore, to ensure a flawless gear mesh that did not result in damage, the worm wheels were not bolted directly to the roots of the propeller blades. If they were, the massive aerodynamic and physical vibrations of the heavy wooden blades in flight would quickly shred the delicate teeth of these worm wheels. Instead, the worm wheel transmitted its rotational force to the blade through a floating cross disc, and this is what allowed the worm wheel itself to stay protected. It essentially acted as an Oldham-style coupling. This cross disc compensated for any axial displacements and absorbed any potential flight vibrations being passed from the blades into the gearbox, and this not only ensured play-free movement, but also a reliable gear mesh, and much less wear and tear on the gearbox and the gear trains running all the way back through to the start of the propeller hub. And that, broadly speaking, is how this Argus variable pitch mechanism worked. Now, I have missed out a few little bits of the system that I could talk about today, but just to get a basic understanding of how and why this system was used, this explanation is enough for the time being. It was an incredibly brilliant and highly creative engineering solution, and by turning the aerodynamic drag of the free-spinning propeller hub into mechanical work, Argus created a system that could automatically adjust the propeller pitch completely independent of the engine's primary power or using an aircraft's electrical system. So that does beg the question of why don't we see systems like this more common in other German aircraft? And one of the main answers you've probably already deduced, and that is that this thing is incredibly complicated. It contained a multiplicity of tiny and highly complex, tightly toleranced parts that were exceptionally difficult and expensive to manufacture, which is not something you really want in a total war situation like you would find in, say, 1941. Additionally, when equipped with the hydraulic control option that I briefly mentioned, it introduced all of the vulnerabilities of rotating oil seals and hydraulic leaks onto what was already a complex and dense mechanical piece of equipment. Another reason was the fact that this was an Argus-designed system intended for Argus-designed engines, which for the most part were lower power and intended for reconnaissance and utility aircraft. The system was never adapted for the higher power engines used in fighters like the Messerschmitt 109 or Focke Wulf 190, because Argus never made engines for those particular machines. These two factors, of course, severely limited the application of this innovative, albeit highly complex system. But despite its complexity, the non-hydraulic version did prove to be highly reliable in the field. It still drove the propellers of thousands of aircraft, including the Arado 96, the Seabold 204, and of course the Focke Wulf 189. So I hope you enjoyed this little technical explanation. As always, thank you all so much for watching, and a big thank you of course to the Patreon supporters and YouTube members who help to keep this channel going. Now this video was a bit of a rush job as I decided to do it last minute, but it has actually worked out really well for me because I'm about to go away, and the video that was meant to be coming out this weekend, I discovered a massive issue with it at the last minute and had to pull it, and I don't have time to re-edit this part of that video, so it can't go up. I am going to be in Cairns for the next 2 weeks, mostly attending Ozarmafest 2026, and doing lots and lots of fun things with the Australian and Artillery Museum. I know it's not plane related, I'm a dirty traitor, but, I like other things other than planes, okay? A big thank you, of course, to our Wing Commander tier supporters, our highest tier members, and if there are any Wing Commander tier or Officer tier members who have not yet submitted their video requests on either Patreon or YouTube membership following the links, please do so now, as those video requests do get priority in the production stream moving forward. Also, if anyone is attending Ozarmafest next weekend, please don't be afraid to come up and say hello. I'll be there with a couple of mates doing some filming, along with just having fun with tanks, but we are actually trying to do some serious work as well. But it's always nice to meet people who are appreciative of what we do, and we'll be kicking around for the entire weekend of the event. So please, come say hi if you see us pottering around. But that is all for today. Thank you all so much for your continued support, and I will catch you all next time. Goodbye.